morning. We continue with the determination of the energy release from an explosion, and let us do the problem which we posed in the last class. We said that we had a volume of 1 meter cube in which we had a gaseous mixture of butane, butane is C4H10, and also with an oxidizer oxygen. Now, we wish to find out how much energy is released from this volume of the explosive. Explosive is you have fuel and oxygen mixed together, which can release some energy. We want to determine that energy. To be able to do this, we said, well, I have the fuel C4H10, which reacts with oxygen, but we do not know the products of combustion. If we know the products of combustion and we also know the reactants, we can find out what is the heat of formation of the products, we can find out what is the heat of formation of the reactants, and the decrease in the heat of formation is the heat of reaction. Therefore, the first step to do this is we must know what are the products. To be able to determine the products, let us for the first exercise assume that the products are going to be CO2, that means carbon dioxide, and water. We assume this. In the second part, maybe a little later in this class, we will see how to determine what are the products. For the present, we just assume this. If we were to assume this, we find, well, I have carbon which is 4, which if it acts with oxygen to form carbon dioxide, I have 4 atoms here, well, I should get 4 of carbon dioxide. I have 10 atoms of hydrogen, therefore, I have H2O, therefore, I should form something like 5 H2O. So, that 4 atoms get balanced here, I have 10 atoms getting balanced here, and therefore, this is the type of reaction. But then how many atoms, how many molecules of oxygen do I require, or how many moles of oxygen do I require? Not molecules, mind you. That means, I have 1 mole reacting with certain moles of oxygen to form 4 moles of carbon dioxide and 5 moles of water. Therefore, if I balance the oxygen atoms, I have 2 over here, I have 8 over here, and I have 5 over here, totally 13. Therefore, I should have 13 by 2. In other words, the reaction should have been C4H10 plus 13 by 2 O2 gives me this, which I can also write as 2 of, I multiply it totally by 2, I get 2 moles of butane C4H10 plus I have 13 moles of oxygen, which give me, now I have 8 moles of carbon dioxide plus 10 moles of water. Now, I need to determine what is the energy. See, I have been able to write an equation provided I assume the products were carbon dioxide and water. Now, I want to determine this. I also tell, yes, yesterday we discussed about heat of formation. We told that the heat of formation of carbon dioxide was equal to minus 393.5 kilojoule per mole. The heat of formation of water at the standard condition, that is the standard heat of formation, here also its standard heat of formation was equal to minus 286.5 kilojoule per mole, and this is for water H2O as liquid, and heat of formation of the butane C4H10 was equal to 1 minus 124.7. Therefore, now we want to evaluate, this is all in kilojoule per mole. We have 8 moles of carbon dioxide, therefore, the heat of formation of the carbon dioxide is 8 into the value here minus 393.5, so much kilojoules, plus I have 10 moles of water, that means 10 into per mole the heat of formation of water is minus 286.5, that is minus 286.5, and this works out to be equal to, if I put it down, I have 8 4s are 32 around and you have 28, therefore, it comes out to be minus 6013 kilojoules. Mind you, this is kilojoule per mole into 8 moles, 286 kilojoule per mole into this is the heat of formation of the products. How about the reactants? Well, oxygen is a naturally occurring element and we define heat of formation with respect to naturally occurring element. We presume both the products and the reactants are at the same standard condition. Therefore, the heat of formation of oxygen is 0, being a standard being a naturally occurring element at the standard condition. The heat of formation of butane is 2, and butane we had the value as minus 124.7 minus 124.7, and this the heat of formation of the 2 moles is 2 into this, which is equal to minus 294 249, I am sorry, 248 to for 249.4 kilojoules. Therefore, what is the heat which is generated in this reaction? Well, the heat of formation of the products is minus 6013. The heat of formation of the total reactants over here is equal to minus 249, and therefore, we find that there is a decrease in heat of formation, that means minus 249 to minus 6013. Therefore, the heat of reaction in this particular reaction, I say enthalpy of reaction or heat of reaction is equal to minus of, that is the decrease. Therefore, I put a minus over here 6013 minus 249.4, and mind you this is minus, therefore, minus over here and minus of minus over here. Therefore, this is equal to plus 6013 minus 249.5, and this comes out to be equal to 5763.6. This is the heat from this particular reaction involving 2 moles of butane and 13 moles of oxygen. Therefore, but how do I determine what is the heat released from 1 meter cubed? I have to determine how many moles are there in 1 meter cube. I know that I have 2 moles plus 13 moles, 2 moles of butane plus 13 moles of oxygen. That means, I know for 15 moles of reactant, what I have, the energy which is got from this reaction is 5763. Now, how many moles are there in 1 meter cube? There are 2 ways of doing. Had I given the initial pressure of this volume as equal to, let us say, 1 atmosphere, and we also told all these things are at the same standard condition, 1 atmosphere and 25 degrees centigrade. I can now write, assuming yes, butane and oxygen as perfect gas mixture of these two being a perfect gas, I can write PV, pressure into volume, is equal to number of moles into universal gas constant R naught into T, and therefore, I can get the number of moles in this mixture. The pressure is 10 to the power 5 Pascal 1 atmosphere. I know the volume is 1 meter cube. I know the number of moles I want to calculate in 1 meter cube into R naught. The universal gas constant is 8.314 joules per mole Kelvin, that is I have so many moles 8.314. T is equal to 273 plus 25, which is 298. This is one way of calculating the value of number of moles. From this equation I calculate, or alternatively we also know that 1 mole of any gas, as long as it is a ideal gas, at standard temperature and pressure has a volume of 22.4 liters, which is equal to 0.0224 meter cube, and therefore, 1 meter cube will contain 1 over 0.0224 number of moles. Either this way I calculate n is equal to 10 to the power 5 divided by 8.314 divided by 298, or directly from the volume, and this will come out to be equal to the total number of moles will be 44.64. Therefore, the number of moles of the reactant over here is 44.6. If I have 15 moles of reactant, I get so much heat. Therefore, in 1 meter cube of the mixture which contains 44.64, I will have 44.64 divided by 15 into the energy for 15, which is 5763.6 kilojoules, which is equal to something like 17152, or we can say it as 17.15 megajoules. This is the way we calculate the energy release, provided we assumed here that we are forming carbon dioxide and this. Therefore, for 1 meter cube, well, I tell myself 17.15 megajoules of energy are getting liberated. Therefore, I am able to calculate the energies, but mind you, we have made two assumptions. We made an assumption in the products formed. Can I not determine the type of products which I will have? And if I have to determine this, well, I need some more definitions, I need to work out with some more inputs. That means I need some more data. Therefore, let us see what are the additional definitions what I require. We determined something known as stoichiometry. In any chemical reaction, when we start learning chemistry with chemical reactions, we define a term known as stoichiometry. What do we mean by stoichiometry? The word comes from the Greek letter stoichion, meaning elements. That is, stoichio comes from stoichion. Metry comes from the Greek word again, metria, which means amount. And when we say stoichiometry, we mean the proportion of reacting substances. Like in this particular reaction, what did we have? We had C4H10, we had 2 moles of C4H10 reacted with 10 moles of oxygen to give me something like CO2, that is, I had something like 8 moles, I had 10 moles of water, that means 8 moles of CO2, 10 moles of water. Therefore, the proportion is 10 and 2 over here, that is, molar ratio is 10:2 over here. Therefore, actually strictly stoichiometry just determines the ratio of the proportion of the reacting elements or reacting constituents. But when we use the word stoichiometry, more often than not, what we use is we presume, when we talk of stoichiometry, we assume that products which are formed are completely oxidized. I require to qualify this. What do we mean by saying products are completely oxidized? In this, let us get back to our reaction. We had the reaction 2C4H10 plus 13O2 giving you 8CO2 and 10H2O. Well, the carbon over here reacts with oxygen, it formed carbon dioxide, it could have also formed carbon monoxide. Maybe it could have also not, it could have just formed carbon itself, maybe it just formed this. If I look at CO2, CO and this, CO is not fully oxidized, it can still get oxidized further to form CO2. Therefore, we say CO2 is a fully oxidized substance. So, also if I consider water which is formed, well, the hydrogen gets oxidized by oxygen to form water. Well, it could still form H2O2, get more oxygen and form hydrogen peroxide. But hydrogen peroxide is oxygen rich, it is an oxidizer by itself. Therefore, we say, well, it is oxidized to form a substance which is neither an oxidizer or a fuel, that is, it is fully oxidized to water. And when we say fully oxidized substances are what we call as completely oxidized substances. That means, when the products are completely oxidized, well, the reaction becomes C4H10 plus 10O2, what we have written earlier was fully oxidized, and this type of reaction is what we call as a stoichiometric reaction. Let me write it again, stoichiometric reaction. Therefore, under the assumption that the reactants form fully oxidized products, well, I say completely oxidized products are formed, and if I presume completely oxidized products are formed, I know a CO2 and H2O are formed, and now I can calculate the energy which is liberated from 1 meter cubed, or if I say so many kilograms, I can convert this to kilograms and find out the energy released by the explosion of this particular substance. But then we still are working with oxygen. Mind you, if there is a spill, let us say at home in your kitchen, I have the cooking gas which is essentially butane, and maybe I have a pipeline which connects it to the burner at home. Suppose there is a leakage of this from the pipeline, that is, or the cylinder is leaking or your stove is leaking, and in the kitchen which has a certain volume, I am able to collect a mixture of, in this case I have a mixture of C4H10 which is butane plus air, it is not oxygen. In practice, whenever a fuel gas leaks and forms a mixture, it is not C4H10 with oxygen, but it is C4H10 with air. Therefore, how do I modify? Now, I want to go further and calculate what is the energy released, let us say in a volume of 1 meter cube, if butane and air are there. And let us now presume that since I have defined the word stoichiometry, let us say I am looking at a reaction between, let us say, butane, we will extend it to other substances, plus air to form fully oxidized substances, namely CO2 and H2O. Therefore, now I need the properties of air to be able to solve this particular problem. Therefore, when I look at air, we say we know air perfectly. Air consists of 21% by volume of oxygen. It also consists something like 78.1% of by volume of nitrogen. It also contains something like 0.9% of maybe other gases like argon, maybe depending on the environment it could contain some CO2, it could contain some helium, it could contain some xenon, argon and all that. These are all, maybe these gases are not reactive gases, they are all inert gases, and therefore, I can combine the nitrogen with the inert gases and tell, well, air consists of 21% by volume of oxygen and 79% by volume of nitrogen. Therefore, volumetrically, one volume of air consists of 0.21 volumes of oxygen and the balance 0.79 volumes of nitrogen. Now, see, I am more interested in moles, whenever we say we write an equation, I say 1 mole, so many moles of air or so many moles of carbon dioxide, so many moles of water is what we are talking of. I would like to convert the volume into moles, and again I look at this particular ideal gas equation. I have PV is equal to number of moles, universal gas constant which is same for all gases, into temperature, and maybe at any pressure and temperature, so long as they are the same, volume, pressure is the same, temperature is the same, this is universal gas constant, the volume goes as the number of moles, and therefore, the moles are proportional to the volume, and therefore, I say 1 mole of air contains 0.21 moles of oxygen plus 0.79 moles of nitrogen. Well, therefore, maybe why look at air? I already have the equation for oxygen. Can I therefore say, well, when I have a reaction involving 1 mole of oxygen, the 1 mole of oxygen will carry along with it 0.79 because I am using air. In air, if I have 1 mole of oxygen, the amount of nitrogen or number of moles of nitrogen I have is 0.9 divided by 0.21, which is equal to 3.76 moles of nitrogen. Therefore, if I were to have a reaction involving air, well, this equation will get modified, because instead of having 10 moles of oxygen, I will also have to carry some amount of nitrogen, and let us see what this equation should get modified as. Let us modify this equation now to be able to put air over here. What is it I get? I have 2 C4H10, 2 moles of butane plus 10 of oxygen. Since I am having air, I am going to get 10 into 3.76 of nitrogen is what is going to form my products. Therefore, now you see I have added nitrogen, therefore, this becomes air and the total moles of air are 10 plus 10 into 3.76, that is the total moles of oxygen and nitrogen in the air, and this is going to give me, we said, well, it is a stoichiometric reaction, therefore, I form completely oxidized products 8CO2 plus 10H2O. Is it 10O2 here? You know, let's balance and see. C4H10, what did I have here? I have 13, therefore, if it was perfectly balanced, it should have been 13 over here, because I have 8 will take 16 oxygen plus I have 10, 26 means 26 of oxygen atoms, therefore, 26, 13 into 2, 26 over here, plus I have 13 over here, then only I can form 8 CO2 plus 10 H2O, and nitrogen being inert, it gets back into the products as 13 into 3.76 of nitrogen. Now, this is my reaction with air. Now, I want to find out what is the energy liberated if I have corresponding to the same old problem, if I have instead of 1 meter cube of I have butane plus oxygen in the proportion such that I get stoichiometric or completely oxidized products of combustion, and instead of oxygen now I add also the amount of air, that is 3.76 nitrogen. For each 1 mole of this I add this. Now, I want to find out what is the energy which is liberated from 1 meter cube. To be able to do the problem, again I do the same process. I want to find out what is the heat of formation of the products. Well, we have originally when I did the problem with oxygen, I had 8 carbon dioxide, 10 water, and now I introduce this. Therefore, these two terms remain the same as earlier, and what is the value I got for 8 CO2 plus 10 H2O, the heat of formation, that was equal to minus 6013. Let us write it out over here, minus 6013. And what is the heat of formation of nitrogen at the standard condition? Well, we presume that we are finding out the difference when both the products and the reactants are at the same standard condition. And what is the value for nitrogen? Well, it is a naturally occurring element, it is 0. Over here for oxygen, it is 0 as earlier, it is 0 over here, it is a naturally occurring element, 2 C4H10. If we go back and see the value, well, it is 2 into minus 124.7, which is equal to minus 249.4. And you know, we see that yes, I have exactly the same value for the products, I have the same value for the reactants, and therefore, the heat of reaction in this case remains the same as earlier, and the value is something like what we had earlier, 5763.6. That means, whether I burn with air or with oxygen, the heat generated in the reaction of the explosive remains the same. But I am interested not in the energy liberated by the reaction, but I want the energy liberated in 1 meter cubed of this volume, and that is where the difference really comes in. Let us now find that value out. We get, yes, for 1 meter cube, we know in 1 meter cube the number of moles are same as earlier. The number of moles of reactant in 1 meter cube is equal to, we had 44.6 moles. You will recall we just said yes, in one mole at standard temperature and pressure has a volume of 22.4 liters, and therefore, this was the value. And how many moles of the reactant do we have which forms this in this case? Now, we have 2 moles plus 13 moles plus 13 into 3.76 moles. Therefore, we find 2 plus 13 into 3.76 number of moles of the reactant is what gives me the heat release as 5763.6 kilojoules. Therefore, if I put this, it is 13 into 3.76, the value comes out to be 2 plus 13 plus 13 3s are 49, I have 48.9, which is equal to 63.9 moles. Therefore, 63.9 moles gives me this. In the volume what I have only 44.6, therefore, the energy which is liberated from 1 meter cube is equal to 5763.6 divided by 63.9 into 44.6, which is equal to, the value is 4026 kilojoules. Now you find, yes, there is a difference. The energy liberated with oxygen was quite high, of the order of 17.15 megajoules, whereas with air the energy release is much higher. Because why does it happen? Because of the dilution effect of nitrogen, the energy density comes down and the energy release keeps coming down. Therefore, for a stoichiometric mixture of any cloud, maybe a fuel and air mixture or any other mixture or any other substance, we are in a position to calculate the energy release. And how do we do that? Well, we just let's quickly summarize the method of doing it. We calculate for any reaction, let's put it as a general form. Well, I have maybe reactants, let's say n moles of reactant A reacting with B moles of maybe an oxidant or oxidizing agent B, gives me, let us say, NP moles of product P1 plus NP2 moles of product P2 and so on. And therefore, what is the energy release from this is equal to minus of NP1 into the heat of formation at the standard condition for P1 plus I have NP2 into heat of formation at the standard condition for P2 plus so on. This is for the products. I say, well, these are the products which are formed. And what is the reactant? Minus I have I again put it in bracket Na into heat of formation of A at the standard condition plus Nb into standard heat of formation B is the energy of this particular reaction. And if I have a particular mass which corresponds to the total number of moles N or a volume which corresponds to the total number of moles N, then I know that this energy is liberated from so many moles in this reaction. Therefore, I calculate for a volume which contains so much moles of reactant or a mass which contains, and this is how we evaluate the energy release from a reaction. Well, this is for stoichiometry, but in practice there is one problem we have. Let us go back and see what is the issue which we could have when we really have a spill and some gaseous mixture gets formed, or if we have something like, let us say we have an explosive like a solid explosive. The solid explosive need not always be in a stoichiometric proportion. It may not always form completely oxidized products of combustion. In which case, let us see what are the other definitions we require. Let us first consider the case of maybe a mixture with air. When we say a mixture, we also talk in terms of mass of fuel divided by mass of oxygen or mass of, let us say, air, because we are considering with air, let us say mass of fuel divided by mass of air. This we call, when it is in the mass ratio, we we call as fuel to air ratio. I could have a fuel reacting with oxygen in any proportion I want. I could also have fuel and oxidizer, which gives me completely oxidized products of combustion, in which case I say this reaction is stoichiometric. Therefore, I can also determine a fuel by air ratio for a stoichiometric reaction. And what is the value of the stoichiometric reaction? Well, the amount of fuel by air, which I say is stoichiometric, whereas in practice it could be anything different from stoichiometric, because as we told ourselves, well, it need not always form the completely burnt products. We define something known as equivalence ratio phi as equal to the actual fuel by air mixture, that is by mass, divided by, let us call it as actual, divided by fuel by air mixture for stoichiometry, and this is what we call as equivalence ratio phi. Therefore, let us complete this, let us determine the value of fuel by air mixture for the previous problem in which we had this stoichiometric conditions. Let us determine this and see what are the variations possible. Let us put down the reaction again, let us calculate this value. We had the reaction was C4H10 plus 13 of oxygen. Every mole of oxygen is accompanied by 3.76 moles of nitrogen. Well, this gave me carbon dioxide, water and nitrogen. If I were to look at the fuel by air ratio for this particular reaction, which gave me stoichiometric products of combustion, the fuel by air ratio is equal to, how much is the fuel? 2 moles into, what is the molecular mass of this? I have 4 into 12, 48, plus oxygen plus hydrogen, 10 into 1, 10, that is the mass of fuel, that means 58 grams per mole is the mass of the butane, into 2 is the value of the mass of this, which is reacting with oxygen, and what is the mass of air? 13 into O2, 16 2s are 32, plus I have 3.76 into 28, and if I calculate this value, it is 58 2s are 116 divided by 13 into 32 plus this value, the value comes out 0.065. In practice, most of the hydrocarbon substances, you take methane, ethane, propane, butane or any other substances, the fuel air ratio would be of this order of between 0.06 to 0.07. This is for the case of stoichiometry, when you have completely burnt products. But supposing, let us say, well, the substance is such that the spillage has happened in the kitchen, I release some amount of butane, the amount of air in the kitchen is smaller or it is larger, I could have a reaction. Instead of this reaction, let us consider another reaction, I put it in a different color chalk, I could have 2 C4H10. It is possible that I have, instead of 13 moles, the amount of air with which it mixes is only 10 moles of oxygen plus 3.76 of nitrogen. This is one scenario. I could also have the leakage is much smaller and it mixes with the larger amount, that means I could also have 2 C4H10 plus I could have 15 moles instead of 13 moles of oxygen plus 3.76 of nitrogen. Well, this is possible. In this case, well, I will have products which are not really stoichiometric, which cannot be oxidized. Well, in this case, I have excess oxygen, therefore, excess oxygen will anyway give completely formed products of combustion, but I will also be left out with this, we will have to do this problem. Therefore, the question is, for this, what is the fuel air mixture? For this, what is the fuel air mixture? Let us put the values down. I put it on this side, I get fuel air mixture when I have the the less amount of air, or it is something like fuel rich or let us say oxygen lean, both are identical, is equal to 2 into 58 divided now by 10 into 32 plus 3.76 of 28. In this case, in the second case, what is the value I get? I get the fuel air mixture actual is equal to 2 into 58 plus now I have 15 into 32 plus 3.76 into 28, and if I calculate this value, the first value, it comes out to be fuel air mixture (0.084), and in the second case it comes out to be equal to 0.056. Therefore, in this particular reaction, therefore, what is the value of the equivalence ratio? Well, phi is going to be, let us put it over here, phi is going to be the value of the actual fuel air mixture 0.084. If the reaction was stoichiometric, I should have had 13, I should have had 0.065, and therefore, the equivalence ratio is going to be something like 1.29. In the second case, wherein I had more of oxygen, the value of phi is equal to, the value is 0.056 divided by 0.065, and this value comes out to be equal to 0.080. Therefore, what is it we have done? Let us quickly summarize this before we go to the next part of our problem, that is to evaluate the heat content. We said, well, whenever you have this fuel vapor mixing with air, what happens is it need not always be in the stoichiometric proportion, that is forming completely oxidized products of combustion. We said, well, you had an equivalence ratio. I plot the equivalence ratio, let us say I draw the equivalence ratio on the axis along this. I tell myself, when I have completely burnt products of combustion, I call it as stoichiometry. Stoichiometric is fuel by air actual divided by fuel by air stoichiometry. Well, for stoichiometry, this becomes stoichiometry, the value of phi is 1. If the phi value is less than 1, what does it mean? I have less of fuel, and therefore, the values between 0 to 1, when the fuel air ratio actually is 0, which means I have no fuel at all, I keep on having fuel which is fuel lean or let us say oxidizer rich, and if phi is greater than 1, I have more fuel than stoichiometry. Well, the second part corresponds to a rich mixture, that means fuel rich mixture, and therefore, the region to the right of 1 corresponds to, let us say, fuel rich, and 1 corresponds to stoichiometry, and this particular region corresponds to fuel lean. And what separates the fuel lean from fuel rich is an optimum which gives me the stoichiometric value. In practice, this is somewhat important because most of the explosives which we deal with are somewhat fuel rich, and therefore, we should have some method of calculating the energy release in fuel rich mixtures, but we could also get a fuel vapor mixture which is sort of fuel lean, and therefore, what I do now is how do I now modify whatever we have done for stoichiometric mixture to be able to get the energy release from fuel lean mixtures and fuel rich mixtures. This is what I want to do now. Therefore, let us revisit the problem again. See, let us quickly summarize though, because these things are to be kept in mind. We tell ourselves, well, I talk in terms of a stoichiometric reaction, I talk in terms of a fuel lean mixture, I talk in terms of a fuel rich mixture. These are given in terms of the equivalence ratio. If the equivalence ratio is greater than 1, well, it is fuel rich. If the equivalence ratio is less than 1, it is fuel lean. Let us do the calculations for one. For fuel lean, that is phi less than 1, let us do an example for fuel rich, which is greater than 1. Let us keep this over here because this is for stoichiometry. Let us proceed further. Let us consider the case fuel lean mixture. That means phi as per this is less than 1. Let us take the same example what I took here. Instead of having this particular reaction wherein I had 2 C4H10 plus I had 13 into air is O2 plus 3.76 nitrogen giving me products. I need to calculate the products. I now say, well, it is lean, therefore, let us presume that the amount of oxygen I have is higher. Let us assume that I have something like 15 amount of oxygen. If it is, that means I have excess oxygen, therefore, when I say fuel lean, I talk in terms of air being more. And what are the products of combustion? Well, I have so much of oxygen, but anyway the carbon will get converted to CO2, the water will get fully oxidized to water here, and I also have the balance of 15 into 3.76 of nitrogen which is left it back. Now, is there anything left? You know, you balance the equation, you find, well, the amount of oxygen what carbon has consumed and hydrogen has consumed is 16 plus 10, 26, and the amount of oxygen I have is 30 over here. That means, I am left with 4 of oxygen which is left, and therefore, in the products I will also have 2 of oxygen. Well, the nitrogen remains the same because it does not participate, it is inert. Therefore, now I have the reaction which tells me, well, I have in the products in addition to CO2 and H2O some oxygen also. Now, what is the energy liberated in this reaction? Well, you know, we have already seen that the heat of formation of oxygen being a naturally occurring element at standard condition is 0. Well, the nitrogen does not play a role, it is also 0. Well, here also this is 0. We have exactly the same thing, 2 C4H10 and 8 CO2 and 10 H2O, and therefore, the heat of this reaction remains the same as in the case of a stoichiometric reaction, and that is equal to 5763.6. But how about the energy release? That is, the heat of reaction remains the same, but now we find that the number of moles of the reactant have gone up. Previously, the number of moles of reactant, that means for this reaction the number of moles was 2 plus 13 into 1 plus 3.76. This was our earlier case. This is with oxygen, we had air was 3.76. Now, we have 2 plus 15 into 1 plus 3.76, and therefore, what has happened? You know, you have excess air, therefore, the number of moles in the given volume have gone up. If the number of moles in the given volume have gone up, then what is going to happen? The mixture is less dense, therefore, we tell ourselves this particular energy is released from something like more number of moles, and this volume has a fixed number of moles which was 46.6 moles, and therefore, the energy release per unit volume or for 1 meter cube volume or for a given mass will keep coming down as the fuel becomes leaner and leaner, and this is to be expected. Let us plot this graphically, which I just now told. I did not put the numbers down because putting the numbers will take some time. We tell ourselves, well, let us put it down a little better, little more with better clarity. Here phi is equal to 1. This is the energy of the reaction. We tell ourselves, as long as you have fuel lean, that is air rich, the heat of reaction remains the same. But if I want to find out what is the energy liberated for a given volume or for a given mass, what happens is the number of moles in the reaction go up, and therefore, for a given number of moles, well, the amount of heat release comes down. A given volume. That means, we are talking of this is equal to the energy per unit volume or for a given volume, this is heat of the reaction which remains stationary. Now, we want to go ahead and calculate, we will do one or two more examples involving some solid explosives such that this concepts gets more clear in our mind. Let us do an exercise for the fuel rich condition before we revisit the fuel lean condition, fuel rich condition. What will happen in fuel rich condition? Let us take another example and let us do this example completely. Well, fuel rich, we said, well, I do not have something like 13 moles for stoichiometry, maybe I will have less. Let us consider 10 moles, which is the example which I considered earlier. Let us therefore write the equation down, 2C4H10 plus, now I have 10 of oxygen. 1 mole of oxygen is in the air is associated with 3.76 moles of nitrogen. Now, I want to write the balance equation. Therefore, what is it I get? Let us presume, like in the earlier cases, I still get, let us say, 8 CO2 plus 10 H2O plus I get the nitrogen. We'll put these down a little later. If I were to get carbon dioxide and water that is completely oxidized as in a stoichiometric reaction, I need something like 16 atoms of oxygen. I need something like 10, I need 26 atoms of oxygen, and what I have here is just 20 atoms, whereas what I require is 26. Therefore, it is not likely that 8 CO2 is getting formed. It is also quite possible that 10 of water is not being formed. Therefore, what could be formed? Could be something like A moles of CO2 plus B moles of CO plus maybe C moles of carbon itself as a solid plus maybe D moles of H2O plus maybe E moles of H2 and so on is what could be formed, because there is not sufficient oxygen to form carbon dioxide and water. Therefore, if I say, well, my products are going to contain carbon dioxide, carbon monoxide, carbon as soot or carbon in the solid form, water, hydrogen and so on, how do I determine the moles A, B, C, D, E when the number of moles of the reactants are given as 2 and 10? Now, I try to do this, I tell myself, well, I can do the carbon balance, hydrogen balance, because the number of atoms cannot get lost. That means, the number of atoms of carbon in the total left hand side and right hand side must be the same. Therefore, I say, well, carbon on the left hand side is 8, hydrogen on the left hand side is 20, well, oxygen on the left hand side is 20, nitrogen on the left hand side is equal to 10 into, that is 37.6. Well, on the right hand side I will also get nitrogen, but nitrogen if I presume is inert, I get on the right hand side 37.6 nitrogen. Therefore, I am really not bothered about this. This comes on the left hand side and right hand side. Therefore, now I can write 3 equations, and the carbon balance equation will now tell me on the right hand side, if I were to write the value of 8 is equal to, I get is equal to 2A plus B, because 2 into A plus B plus I have C is carbon balance, hydrogen balance is equal to, I have 2D plus 2E, oxygen balance if I were to write, I get is equal to, well, carbon balance is CO2, A CO2, therefore, it is just A plus B plus C over here, hydrogen balance is 2D plus 2E, oxygen balance is equal to 2A plus I have 2A plus B and plus D. Therefore, what is it? You know, I have unknowns, which is 1, 2, 3, 4, 5 unknowns. I have only 3 equations. There is no way I can determine the moles in the product. Therefore, it becomes difficult for reactions in which the equivalence ratio is greater than 1 or which are fuel rich substances or fuel rich reactions to be able to determine the moles of the product. I cannot determine the products. I have no way of simply balancing it and determine the products, and therefore, I need some more information. And one way of doing it is, we tell ourselves, well, I have a reaction taking place, the energy release heats the products to a high temperature. At the value of high temperature, the products like CO2, CO, C, H2O, H are in equilibrium, and when things are in equilibrium, well, I can use thermodynamics to calculate the particular ratios here. That means, I say Gibbs free energy is equal to enthalpy minus temperature into entropy, and for equilibrium Gibbs free energy is a minimum, and therefore, I can use this and calculate, provided I know the temperature, but I do not know the temperature because I do not know the energy release. Maybe through an iteration process, it is still possible for me to calculate this, but the process is rather cumbersome. Maybe we will do it towards the end of the course, when if and when we get some more time of calculating using chemical equilibrium analysis, but I find yes, there is a simpler way of doing it, and that simpler way is somewhat approximate. It is not really rigorous, it is very approximate, but based on my experience I find that this approximate method gives out values of energy release which are quite reasonable and fairly accurate. Therefore, what is it I am going to say? Well, can I do this approximate analysis? We will just indicate how this approximate analysis is done. And since I have more number of variables than the number of equations, I tell myself, well, in my equation, in my reactant, I have carbon and hydrogen. All of us know, well, charcoal or carbon takes time to burn, it is not as reactive as hydrogen. Hydrogen is a very reactive substances. Therefore, we can tell ourselves, well, hydrogen first just gets consumed, it is much more reactive. First hydrogen gets consumed and then carbon gets consumed, and therefore, we make some assumptions. Let us just list down the assumptions, we will do the calculations in the next class. And the assumptions which we make are the following. Whenever I have a fuel rich reaction, I tell myself, well, the nitrogen in the reactant gets back as nitrogen, that means nitrogen is inert, it is gets back into products as nitrogen. Then if I have in the fuel carbon and hydrogen, hydrogen being more reactive, first reacts with oxygen, it tries to consume as much as oxygen as it requires to form water, and after forming water, if some oxygen is still left, the leftover oxygen goes and reacts with the carbon over here to form carbon monoxide, that means leftover oxygen reacts with carbon to form carbon monoxide, and if oxygen is still left, part of this carbon monoxide reacts with the oxygen which is left over to form CO2. Therefore, we have some steps, and let us do a model problem in the next class, and then we will be able to find out how how the energy can be calculated for fuel rich mixtures. Well, thank you then.